All right, well, thank you for filling out those evaluation forms. I will fill those. We've got some useful information. One thing I wanted to act on right now, since there were no names, and since I haven't actually trained a machine learning model on your handwriting, I didn't know who this was, but someone did point out that, and this is certainly true, for many of the homeworks, I didn't have submissions set up on Gradescope until late. And so then this person said that they forgot. They had had it ready before, but then forgot to submit it that morning once it was actually open. And so if you're in the position where you've actually done the homework but just hadn't submitted it because in fact it wasn't open, let me know and we'll do that. Okay. After class. If I could get all your midterms up here, that would be great. I will have them graded by Monday. On Monday, we do have a quiz scheduled. That's going to just be about stuff that we go over today. There's no associated homework. You guys don't need another homework. So in fact, I think there's only one or two left in the course. But there is a quiz, and then the assignment is due Monday night at 11, right? So what we're going to talk about now is recurrent neural networks. So recurrent occurring over and over again. What a recurrent neural network is designed to be able to handle is sequences. So it can handle sequence input and sequence output. One way to think of this is as input or output that is of unknown length. Okay, you don't really have ahead of time a particular size for you to be input or the output. So we've got an image as input. That's some fixed size that we deal with. Right? We have a network that's 160 by 160 or something else. I suppose if we wanted to support multiple size images, we could say we have kind of an unknown length and feed it in pixel by pixel. That'd be kind of weird. So give me an example of sequence things. Sentences. Or let's even just say words in a sentence. Okay, or words in a document. So those would be items in a sequence, words in a sequence. Right? And we don't know ahead of time how big that's going to be. Certainly if we look at sentences, they're of unknown lengths, although there's some practical upper bound probably on that. But if we look at, let's say, words in a document, and the documents can be as small as one paragraph, let's say, and as large as hundreds of pages. We dealt with dealing with words a while ago when we dealt with sentiment review in terms of looking at movie reviews and deciding what's positive or negative. How did we deal with that? We did what? Yeah, so we created a bag of words. And what did that do to the ordering? What happens if the original ordering is what I mean? Yeah, we completely lose the original ordering. And the ordering matters, as they say, sort of, dog bites man is not much of a newspaper headline, but man bites dog really is. And so there the ordering matters quite a lot. So let's look at some examples. Here's one input. I'm trying to show here a waveform. All right, so we record some sound, let's say some speech, and perhaps we pre-process it in some way. Maybe run a fast Fourier transform on it. Unlikely we're going to have the actual raw audio, but possibly. And let's say we want to recognize the word Alexa. Okay? So this sequence of input would be a sequence of, in this case, let's say, we'll just say sequence of audio samples. So we're going to have, it could be 1 second, it could be 5 seconds, it could be 10 seconds, don't know, but it also happens pretty often. So there's a lot of these audio samples. And what do we want to know? Rachel. So we're trying to find Alexa, but we want to know if the user says, if the word Alexa is said in here. So what sort of output do we want from this? Do we want a single output?
Just to know if it is said.
Well, I guess that's true. So if we only want to know if it's said, then I guess yes, a single output would do. Let's say we want to know more than that. We want to know when they say it.
We have like a vector of like time points and then a one where they say it.
Okay, we could have a vector of time points, or we could actually just have a vector of time points, one time point for every input. Right? So we could have a parallel output to the input. So the input would be audio samples. And the output can just be no, 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 no. It's not Alexa, not Alexa, not Alexa. Yes, when they say Alexa. So we could have as our output zeros and ones. And then, so this is no Alexa. And then when they say Alexa, then we put in a 1. Yeah.
What's the time interval? How are we dividing that?
What's our interval? It's whatever our audio samples are. So maybe it's
So
a millisecond.
a single zero means that they didn't say Alexa in what period of time?
They have not said Alexa, let's say, in the last 50 milliseconds. So let's say this is 1 millisecond samples. I don't know. And we could just, and a single one seems like it's very strict. Like, here's where they just said, so let's say Alexa's going from here to here. This is Alexa. Okay? So maybe we'll put some ones here for a while. So this is kind of the range in which they said Alexa, and we just slot there. Does that kind of make sense? Okay, this is perhaps a more complicated example than I should have used as an initial example. So let me give you another example. Let's say we have a picture like this. This is the input. Is this a sequence? No, it's a picture. But we want the output to be a house, the sun, and a happy face. So we're captioning this picture. The output is a sequence, right? A sequence of words. Or I suppose if you broke it down even more, it could be a sequence of characters. You could look at it as. So this is a sequence of words. This is a sequence of yes, no. That's the way they like it. I would like you guys to, for about 3 minutes, in pairs of 2, come up with 3 examples of problems where you have either a sequence input or a sequence output or both. Okay, starting now. And just pick one of these guys who are doing this. All right, one more minute. All right, that's not a full minute, but we're done. All right, so go through and give me one of your notes.
We talked about like monitoring, like having snippets of a heartbeat over time, and then looking for some sort of activity.
So heartbeat, heartbeat monitoring to some sort of a noticing event. Right? Okay. So the sequence data is the input,
Yeah, and depending on what
possibly the output. Okay. All right, language translation. My name is Neil. To Mayamo, thank you. Mayamo, is that right?
We did sequence of quick actions, I think.
Who came up with that idea?
Right?
Okay. So poker actions to
So what the next thing that you should do, or what to do.
next predicted action or next action. Okay. So clearly poker actions agree some sequence being.
Like temperature, weather patterns.
So weather,
Which would be similar, like predicting
temperature record to, and you were doing a prediction? Okay. So general time series prediction possibly, all right?
music.
Say more.
Like, I think we were talking about jazz music, like being able to like continue on a phrase or something like that.
Okay, so let's say notes to next notes. All right.
We were talking about
Speech to text. Speech is clearly sequence data, and text is sequence data. All right.
Like detecting anomalies or like malicious activity in like a sequence of actions or like action on a website.
Okay, so actions. Let's say on website. Let's just say anomaly detection. Right? That's not kosher to do?
They had vibrating wristbands on the players. They would decode it and then send the signal to the players to know those things.
All right, so sorry, so what do we have? So what's our sequence input?
Sequences is like image, like the fingers thrown on video, and then the output is like the order of fingers thrown.
And so they have like a long sequence?
So they can do it from like 3 to 6.
Okay, so when we get in the number of 3 to 6, it's likely we might just say we're going to just use a fixed length, and we'll just pad out the last few, just saying nothing happened. So sign 1, sign 2, sign 3, sign 4, nothing. But nonetheless, it is a sequence. So what is it? Stealing signs? Is that what we call it?
Yeah.
Right. In baseball. All right.
Looking at it, if you took like sentences as input and tried to categorize what author it might be from.
Okay, so sentences, something like authorship. All right, so this might help you say who actually wrote Shakespeare's plays. Yeah.
So I was thinking about like signals, and then we can maybe look at like whether this signal contains what we're looking for.
Signal, like just general signals? Signal processing of some sort?
Yeah.
Okay, so signal processing this kind of subsumes, let's say, heartbeats to events, and temperature record to prediction was slightly different from events. Right, so signal to events. General description of events.
Like processing audio samples to tell you what song it is, kind of like Shazam, like put in a song and it will give you out the
Sure, song to title, let's say. Okay.
We're doing object detection. Video.
So video to object detection. All right, so question number 1, which is the sequence? Okay, so this is a sequence of still images?
Yeah, and I give you a sequence of where it's like
Sequence of where? All right, that's fine. One that came up to me, speech to text is a good one, and then just flipping it around, text to speech is also another pretty valid sequence to sequence transformation. So these are the sorts of things we're trying to do. Another thing we might want to do is, and actually that we will do in C, something like generate some text in the style of Shakespeare, or in the style of Hemingway, or something like that. Or maybe you might seed. So starting with this, once upon a time in Claremont, and then fill that in the style of Hemingway, let's say, or the style of someone else, or the style of Reddit, or some particular subreddit. Okay. And where did we get? Oh yeah, the language translation is very popular. Like some of the big ones is language translation, speech to text, all of that uses recurrent neural networks, and all's gotten very big in the last few years.
One of the things we talked about is like autocomplete. I think like Gmail has this now.
That sequence, that's a good example where it's clearly not just using the previous word, right, which is not a sequence. It's using what you've typed so far. Well, yeah. As far as we know, also using everything you've web browsed in the past, anything else. Okay, so that's our problem statement of what we're trying to solve, is sequences of stuff as input and possibly sequences of stuff as output. So basically, a possible sequence is input and a possible sequence is output. And we have no bound, no particular bound on those sequences. So here's kind of the idea of what's going to go on. We're going to have a box. This is our recurrent neural network. And at time 1, so we're going to actually do this in order. We'll call time order, time steps. Okay. So we're going to do first time step 1. And let's do, probably what we do. We'll do authorship. Sentence is authorship, okay? Because I want a mini to, so this is a mini to 1 correspondence, right? We got a sequence as input and a single picking things up. So we're going to feed in now our inputs, one item at a time. So at time step 1, we're going to feed in X. Just remind myself for a moment of terminology, what I want to be using as symbology, so to stay consistent. Yeah. So I'll just use subscripts for this. So X of 1 is the first element of X. So X is going to be a sequence. Twas, Grillig, and the sliding. Thank you. Toes. Is that right? Slidey toes. The gyre and gimbal on the wave. Into the Borgo. And the moment south Gabe or upgrade? I don't know. Anyway, so we'll have to figure out who this is. I don't know, but this is what we're going to feed in. So we're going to feed in twas, right? That's going to go into our box, and our box is going to hold some state. So this is an RNN, and it has state. And when we feed it twas, it's now got some new state. So it had some starting state, and now it has some new state. And now we're going to move our way to time step 2. And we're going to feed in the second one, Brillig. Now let's even stop here. How the heck are we passing in twas? Like, how will we actually get that as input into this neural network? How have we done it so far? When we looked at feeding in, for instance, our bag of words. Yeah.
We input both at the same time.
We did what?
We put both of them in the vector.
I'm talking about a single word, so I'm talking about the twas right now. How do we feed in twas? So I skipped over a step. When I said X1 goes into the network, like, how did we actually get in these 4 characters?
Can we like assign each character a index and feed them as an array?
If we want to feed in each character, that's a possibility. So if we want to do character at a time, we have one of 26 different characters we need to feed. Well, one of however many characters our character set has. But if we want to do words, then what we'll commonly do is have a big list, right, of all the words. This is a little weird example because our words are not very meaningful. So it's not a great example for this. Let's, in fact, change it so we can do word approach. We'll talk later about a character approach where we can handle any weird words that we wanted. But let's instead change our example to the white whale looked hungry. Right? So in this case, we have known words. So the first word that we're going to put in is the. And we can just make a big list, right, of all our words. Let's say 1 to 100,000. And somewhere in here will be the word the. And we can make this, 9, 5, 6, 2 is the its index. And we'll just have every single word in here, right? Does in here, white somewhere, and so on. And so when we feed in the for x1 at time step 1, what we're actually feeding in is a one-hot encoded 9562. So what we feed in is a one-hot encoded. So we know how to actually feed this network. We have no idea how this network is working, but that's okay right now. Now we're going to move to x2. x2 is going to be the word white. It has a slightly different one-hot encoding. This RNN has state. We don't have any idea right now how it is we can actually maintain state, but we're going to assume it's some stateful box here. And so we feed in the one-hot encoded. We feed in white one-hot encoded. We feed in whale one-hot encoded. We feed in look one-hot encoded. We feed in hungry one-hot encoded. And then we're done. Right? We got to the end of our snippet of text that we're trying to identify. But somehow we need to tell it, we're done. Like, we've reached the end. Okay? How could we do that?
We can have a one-hot that corresponds to like.
Sure. We'll have a special end. All right? So we'll feed in x1, x2, x3, x4, 1, 2, 3, 4, x5, and x6. And x6 is going to be n. So time step 1, 2, 3, 4, 5, 6. And now we get our output from here. So this better have some way to get output. So we're going to have as an output here, we're going to be interested in y sub 6. That is actually, it has an output here at every time step. We're just ignoring it for the first 5 time steps. And the 6th time step, we're going to look at it. And we're going to say, okay, what is the author? And presumably, it has some list of, I don't know, 9,000 authors. And it's going to give us a softmax of those possible authorships. Right? So one of them is going to be Melville. That's what I was thinking of. But another might be, what else could this come from? The white whale and hungry. I don't know, that might be from the Bible. Jonah, but I don't know who that author is. Well, I suppose ultimate authorship. And we have all the other possibilities here as well. Hemingway. So we got this box. It's got an input and it's got an output. Okay? We can read the output whenever we want to. In this case, we only care at the very end what the output is. And so therefore, we will feed in our words one by one by one. Every time we feed it in, its internal state changes. And its internal state changes and internal state changes. It's outputting stuff. We're not looking at it until we get to the very end. And then we look at it. We get this 9,000 vector softmax. And what can we see what it is? So that concept makes sense. That's how we get stuff in. That's how we get stuff out. Let's look now at sequenced output with a single input.
So this isn't training at all, right? This is inference. Like this whole process, there's no training happening. It's all just inference.
We're right now just looking at a box that has input and output, and we haven't talked yet about exactly how we're going to train it. We're going to still be doing backpropagation. So the basic idea is we have some input, we have some output. The output will feed into a loss function, and we'll be able to do some training, changing basically how this network works. So the idea remains the same, although there's some peculiarities we have to deal with. So let's look at another example. which is captioning. So we feed into our RNN at time step 1. Our thing we want captioned. Right? And actually, what we'll probably want to do is not directly feed this into our RNN, but instead go ahead and do some convolutional neural network on this to just come up with a sequence of features. Right? Think of our CNN with our various levels, and then at the very end we normally have classification. Well, somewhere like here, that last level contains all the abstract information we have about this picture. And so therefore, we have this CNN. Let's see. So we have the CNN. This is our last layer. We'll feed this last layer. That will be our input to here. So really what's going to happen is our x1 is going to be our picture. We feed it in here to pre-process it. And this is our processed. Let's call it x prime. So 1. Okay. We could just put this neural network kind of right into the RNN, but it's easier for us to think. We already know how the CNN works. We know it's going to come up with this vector of values at the last layer, and we'll just feed that in. So this is pre-softmax. If we're looking at a classification problem. So it's, just remember when we did the style problem, the neural style transfer, that we said trying to compare content between two images. The way we do that is we look at the very last convolutional layer, and that's what we'll compare. Same idea here. That's what we're grabbing. We're grabbing the content. So presumably there's going to be some information that there's a sun and a happy face and a house in there. There certainly wouldn't be in the first layer. So we'll feed that into here. This is x1 prime. And then we're going to get out y1, y hats of 1. Right? So we feed in the picture, and it's going to spit out a word. In what format will this word be now? Would you guess?
The one hot encoding.
Sure, one hot encoding, except actually a softmax, right? So it'll be a softmax against whatever our vocabulary is. Maybe we use the same 100,000 that we had right over here. Maybe it's a different vocabulary. We have some vocabulary, possible words, and it will give us a softmax across all those. So the probability, first word is whatever it is. So we'll get out of y. So maybe the probability of A is 0.7. So that means our first word is A. And then we go to the next time step. Do we feed anything in? No, we already fed it in. Whatever it needs to know about this picture is saved inside its state information. Okay. Its state has changed after time step 1, and now it's in time step 2, ready to output another word. So we're going to now get, at the next time step, y2. I'm showing these as separate arrows. They're not really separate arrows. There's one arrow. We have an opportunity to input at a time step and get one output at a time step. So one input, one output. And the next time step, one input, one output. Next time step, one input, one output. In our case, we're going to feed an input at time step 1 and get one output. And then we're going to not bother feeding any input to the next one. So we'll just get an output, an output, and an output, and an output. And how do we know when we're done? Nick? Ben? Anyone? Daniel?
Maybe outputs like the end.
Yeah, that's the same thing we fed in our input to tell it that we're done. It can generate on its output to say it's done. Right? So it can have a special word that is end. it's really some special entry in that large list of words. Right? Not actually the word end, because it might need to use the word end, but some, index 0 means end. So it's going to feed it out at time step 1. Y hat 1 equals A. Y hat 2 equals house. There's no house there. A happy face in the sun. And so 3, 4, 5, 6, and 7. Does that make sense? So we've got this sequence, and it can be of arbitrary length. We just sort of have to know when we're done. So we have to know as far as input when we're done. So we're going to need to say in some way that we're done. And we have to know as far as output when it's done. So we do that with some special coding, special signal.
So each y-hat is dependent on the y-hat that's so it's like it has to be done sequentially?
It definitely has to be done sequentially, yes.
Okay.
So it is this black box is keeping track, I just said these probabilities, and now I'm going to have a different set of probabilities and a different set of probabilities and a different set of probabilities.
And then in if the input is also a sequence, then everything would come into the RNN for each time step.
Okay. Let me go ahead and unroll it, because I think it'll be clearer. So this is the rolled up version, and that's how it's actually implemented, but it's easier to look at it in an unrolled view. So we're going to have time steps going to the right. So here's our RNN. We have x sub 1 here, and here we have y hat sub 1. And then the way that the state is maintained is that there are actually a feedback loop here. So there's some output that comes out of the RNN at time step I and comes into the RNN at time step I plus 1. So that's the state information that gets passed. We're representing this. That loop turns into this arrow from time step 1 to time step 2.
Single word after that time step, or the whole sequence to this point? I guess more asking like what gets fed back in.
So the y-hats are actually these probability vectors, right? These softmax vectors of, if we have 100,000 words in our dictionary, a softmax over 100,000, telling us probabilities of each word, probabilities of each word, and so on.
So looking at that through the lens of probability vector, like we see it as a word, but it's probability vector.
It's probability vector.
The input at any given time step is only the probability vector of the previous word.
So the inputs, this is an interesting point. When we're generating, so let's say we're actually generating data, we get this probability vector here, right? So the probability that's starting with the word A is, let's say, we'll just do a very small example. So let's say the probability of A equals 0.7, and the probability of sun, let's say the, equals 0.2, and the probability of happy equals 0.1. And then everything else is 0. If we have this probability distribution across words, and we're trying to generate text, there are two ways we could use this probability distribution. We could either take the max and just say, if this is the probability distribution, then A is what's getting output. It's an alternative we could use. Say more?
Like, I don't know if it makes sense to output like more than one word, but if
It wouldn't make a lot of sense to output more than one word.
but then, or, yeah, then I'm not really sure, because I'd say the probability is over some sort of threshold, so maybe it's not.
What if we flip a coin? We flip a 0.7, 0.2, 0.1 sided coin, right? So we flip a coin, 70% of the time comes up as A. It's a 3-sided coin, I guess. And 20% of the time goes with the, and 10% of the time comes up with happy. So usually, we would choose to output A, because that's a high likelihood thing. But we might output happy as the first word. Because there's a non-zero chance that a good caption for this starts with the word happy. Right? Because, right, so, the question, it was your question about the feeding back in, right? All right, so, here, we will have the picture as our input. Here, we will have, and it's not really a picture. This is, let's say, picture features that we've extracted from CNN. So picture features. Here, the RNN doesn't actually know which word we're choosing. It gave us probabilities. It gave us some high probabilities and some low probabilities, but it doesn't know which one we actually chose. So it would actually be useful to feed into here the word that we input. Does that make sense? And similarly, at this time step, it'd probably be good for us to tell it what the second word that we chose was. Because it actually doesn't have that information. It's not part of its state. It's what are the words that we've chosen to output so far in this generative model. So we would augment the input with the word we chose in the previous time step. When we get to this time step, what would we be feeding in? Y hat what? N-1. But what if this guy needs to know, in order to output the probabilities for here, all the previous words, not just the one with the previous time step? We could make a matrix, but the fact is, it already knows all the words. We already told the RNN what the first word was, and what the second word was, and all the way to the n-1th word. And if it was important to it, it could have kept it in its state. So it's got all the information of what all the previous words were.
Isn't there some issue with like because we're doing this in a specific order that I guess similar to like when we were training like neural networks, you gave it all like, one class or something, then it's gonna just always predict like that one thing.
Yes.
So in this case, like it's something it deems something like some word or something isn't important, but then like in this last thing, it's actually supposed to be really, really important. Is there any way, to get that back and like, edit that more?
So I'm not quite sure I understand. So tell me more about what you mean.
Yeah. So I guess like you're saying like you're putting each of the words in like remember. So the second one is in the first one. The third one is in the second one.
Yeah.
And if it's important, that's gonna be incorporated into the state. But isn't it possible that like at the very end, the second word which we deemed at the time is not important, all of a sudden becomes very important because of the very last thing we do.
I see. So we get to this time step. We wish we knew the second word, but we kind of forgot it.
Yeah.
Is that what you're saying?
Yeah.
That could be an issue. There is an issue of just forgetting. As we move from time step to time step to time step, it's hard to remember stuff from way long ago. So we will look at a mechanism that's added to RNNs called long short-term memory that allows easily saving information and just having it pass along until it's needed. Okay, so that's something that's an important question. It's kind of like, we think of it as a vanishing gradient as we move from way along in the past. Kind of the same idea, but it's hard to remember things in this single state. So we have this special machinery to save things for long term.
So this horizontal arrow that is like passing a state from one time step to another, is it passing state in the sense that it's literally like another input to the network, or is it passing state in the sense that when you
It's literally another input.
Okay, so it's not like the neural net saves its state in the sense of like the weights or
the weights are not changing. So I'm assuming we kind of have a trained network here. So we've got some weights. We haven't even seen how the weights interact with anything, but we have fixed weights. So it's not like we're changing the weights to remember.
So just another input.
So it's not like the way we remember things in our brain, right, which is kind of changing the weighting of synapses and so on. You had a question?
So it might be too specific, but I mean, we have more features than the number of words in the caption, I imagine. So how do we like get to the stage of combining the features together to get one word? For example, like the happy face. Imagine there's like 2 dots and then there's
Yeah.
a mark.
Well, so we fed that, remember, through a CNN. So a CNN could have captured the information kind of about there being a happy face and about there being a sun and a house if there was a house. And so that would be in this vector here. This vector would have enough information to be able to capture that. When we do our training of this all, we would be training this network and the CNN network as well to make sure it is capturing exactly the information the captioner needs, the RNN needs. So I'm going to, in just a moment, I will actually show you the very simple formulae for the RNN, and we can see what the inputs and outputs computationally are.
So in regards to the state change, does that depend on the output of like that time step, or like the forward propagation through it, or like what?
The state change doesn't. I'll just show you in a moment.
I still don't quite understand why we need like the previous output from the recurrent neural network, because this, what if like x1 and x2 are just completely like independent? So how is like the previous output helpful in our case?
Let me give you an example. Let's say let's just say we have some probabilities. Okay, so 0.7, 0.2, 0.1, and five, 0.3, and 0.2. Okay, so I tell you these are the probabilities for the first word, and these are probabilities for the second word. Right? Ignoring the captioning of numerals, just maybe I'm just telling you I've got this sentence you could generate, or let's say a different way, a corpus of sentences, and the probability of the first word is this, and the probability of the second word is this, and so on. So if I just take the highest probabilities, I'm going to get, let's say, the and happy, which actually looks pretty good, right? Another alternative would be, I might say, happy is the first. I'm going to do an even simpler example. One moment. A and un. All right. And we have here happy, which is 0.5, and anxious, which is 0.5. All right? If I know the first word is A, can the second word be anxious? It just doesn't work in English, right? We can't say A anxious. We have to say an anxious. So we have to know what first word is in order to come up with a correct second word, even if only for things like this with articles matching. Okay. For meaning as well, that might be necessary, but even just for articles matching. So I know if the word was A, I'm going to just, any possibilities I have here for the second word of words starting with a vowel, I'm going to say it can't be that, right? So when I feed in the recurrent neural network with the fact that I spit out an A, the fact that we chose an A here affects the probabilities of the next word. probabilities for word 2 starting with a vowel are extremely small. Whereas if I chose an N here, in P data N, the probabilities of words with vowels become high, and the probabilities of words with consonants become low. So we have this context. This is really the probability. So this is the probability of Y1, is the first word. This is the probability of Y2 given Y hat 1. Given, and I really shouldn't say this here, so let's adjust our terminology. Y hat 1 is a probability distribution. We're going to call this word 1. That's really better. Okay? So word 1 is from Y hat 1 in some way. Either we chose the max, or we chose, based on the probabilities or something, but we chose a word. So this is really the probability distribution for word 2, given we've chosen word 1, given that word 1 is what's first. So given that word 1 is an, what are the probabilities for word 2? Does that help? All right, so let's look at the simplicity of the RNN in terms of the equations. So our RNN has coming in x of t, because this is time step t. We have here h sub t. So h sub t comes out, and y sub t comes out. Really y hat, because it's a prediction, but that's okay. We're going to have a matrix here. We're going to have a matrix here, and we're going to have a matrix here. Okay, weight. So we're going to take xt and have a weight matrix. I'll call it W instead of M. And these are distinct weight matrices. So I'm going to call this one XH. Okay? Yeah.
We're using W for words.
These are lowercase w's. Or if we write them very randomly, they look like omegas. So our big capital W's, we have predetermined have to be our weight. So we're going to take our input times a weight matrix. We're going to add that to the output from the previous time step. The output from the previous time step is what? This time step is t. So the previous time step, t minus 1, and the output is? Say it again. So, I'm sorry, the output of the previous time step, the state from the previous time step. So H, I was unclear, I apologize. H is our hidden state. So the hidden state from the previous time step is H t minus 1. What weight matrix are we going to multiply by? This weight matrix. We're going to take the previous time step and multiply by this weight matrix, which we're going to call WHH. Yeah.
So why, if we use h of t minus 1, what is h of t? Is h of t the hidden state from this time step?
Let's try this. If we unrolled it, we'd have h of t minus 1 coming in, and we'd have h of t going out. When it's rolled up, it just goes back on itself. It's easier to think of it. Here's h of 1 coming out of here, h of 2 coming out of here, and so on. Is that?
Yeah.
So, in fact, maybe I will just write this unrolled. So I'm going to put WHH here, and I'm unrolled. So this is all whenever we multiply by weight matrices, we always add a bias. I'll just throw in a bias here for H. What else do we normally do after we do matrix multiplications to try and add some nonlinearity? Say again? Yeah, we do some activation function G sub H. And what does this equal? This equals H sub T. So that's our new hidden state. How do we get our hidden state? We take our current input, matrix multiplied, our previous hidden state, matrix multiplied, add a bias, apply an activation function. Questions on this? Yeah.
What's the last W?
What's it next to?
Output.
Yes. So we're going to use that for output. But this gives us everything below this output line. This tells you how the RNN is going from step to step to step to step to step to step to step, continually changing its hidden state based on the previous state and based on the current input. Same. This is an activation function. Right? We've used G as activation function. Right? So this is an activation function for H. So that's it. How do we do the output? What's the output going to be based on? Hidden state. So therefore, we're going to take the hidden state at time t, which we just calculated. We're going to multiply it by W, what should we call this? W sub what? We call this one XH because it takes an X and gives you an H. This one is HH because it takes an H and gives you an H. That is, you get multiplied by an H and you get an H. So what should we call this one? HY, because it takes an H, gets multiplied by an H, and gives you a Y. What do we do to it as well? We'll add a bias, so Y, and we will apply an activation function. Maybe a softmax, maybe sigmoid, maybe ReLU, who knows? G sub Y. And this is Y sub T. That is all an RNN is. Until you get to the more fancy long short-term memory and so on. That is a recurrent neural network. Yes?
So eventually the state encompasses both the current input and the previous state?
Well, if we look at H sub T, we can see it's a function of H sub T minus 1. H sub T is a function of X sub T and H sub T minus 1. H sub T minus 1 is a function of X sub T minus 1 and H sub T minus 2. So H sub T is a function of all the X's. Because if we just expand this, we'll just get this function and we'll see, oh yeah, there's an X1, there's an X2, there's an XT minus 1. All the X's are in there. Go ahead again.
But then just to clarify, the output from at the current time step is dependent on the state at that time step. So the first thing we do is compute the current state.
Yeah, we compute the current state, and then we output based on that current state, which is important because you certainly want the current output to depend on the current input. Other questions? So if let's go ahead and expand this computation. Let's look at H sub T equals G. I'm going to ignore the of H sub H, so we don't have to write so many things. I'm going to just kind of look here. This is X, T, W plus H, W, H T minus 1. And I'm going to know the bias. I don't care about biases. Call me unbiased. So anyway, and then if I just expand out H sub T minus 1, I get G of X T minus 2 WXH plus H T minus 2 WHH. And if I keep going, get this one. This out. E to t, xt, t minus. Yes, I just skipped the time step. Thank you. And then if I expand it again, I get t minus 2. Expand it again, I get t minus 3. Oh, good. Thanks for that.
Wouldn't the h stay t minus 2 though, because you're supposed to go one less than that?
Yes, thank you. That's a t minus 2. If we look at this function with respect, let's say, to x of 1, we have a lot of matrix multiplications that occur way back here, right, to get to W1. So it's no wonder that it might be the effect of x1 is kind of lost on this, right? If this repeated matrix multiplication leads the values to get smaller and smaller, then the effect of x1 will just be lost. So it's analogous to this idea sort of a deep network where it's very hard to push the gradient all the way back, 100 time steps, 100 layers. Similar here, it can be very hard to maintain x1 in the state for 100 time steps. So that's the motivation for long short-term memory cell that we're going to look at after Thanksgiving. Yes.
Do we still need a W, like the basic state HH outside of this?
All right, let's look at this. All right, we've got this. We're going to G, xt, wxh plus ht minus 1. We know ht minus 1 is this. All right, everyone likes this now. All right, so we can see that we're going to be multiplying by WHH. If we're going back to x1, we're going to be multiplying WHH to the t minus 1 power, and then multiplying it by x of 1 to get that there. So WHH to the t minus 1 or t minus 2 is going to happen. So if this turns out to be very small, then we just lose the early values. All right, let's get started on backpropagation. Basically, backpropagation for recurrent neural networks is nothing special. It makes sense to look at it in the unrolled view. So let me unroll it. And it might be tempting when you look at this unrolled view to think of this as layers of a neural network. And in one way, you can think of it like that. But the key thing to keep in mind is you have the RNN. We have H1 coming out of here. Actually, one question is what comes in the beginning? What's the initial hidden state? Because our formulas take in the previous state. So when we're calculating H sub 1, we need to know H sub 0. What would you like to use? Okay, so it could be identity, matrix. Sorry, not identity. Actually, what do you mean by identity? All ones? What does H1 look like? What's its form? What's its dimensions?